Welcome to another tutorial of ProfLearn YouTube channel. In this particular video, we are going to see questions that you really need to work on so that when you're going to do your May June exams, you are in a good position to do it while smiling. So we are going to look at the first question here. You are told the graph shows current I varies with the potential difference, and then we are supposed to state which component that represent this particular graph that we are having at this given point. And we can see this is a resistor at constant temperature because the graph is straight. So if we are talking of a graph of is going to be, for a thermistor, is going to look like this, and high voltage characteristics for a diode, you'll have a graph that looks like that. So you need to know the graph of a diode, graph of a thermistor, graph of a conductor, that is a ohmic conductor, and also a graph of a filament lamp. Those are the graphs that will be tested when it comes to AS physics, that is unit 2. Now we need to look at the next question here that it says, monochromatic light travels through air and enters a glass block. Which of the following quantity does not change? Frequency does not change, speed, that case. The ray of light approaches the boundary between air and glass as shown there. The angle of incidence is I. Which of the following statement is about total internal reflection is correct for the ray of light at its boundary? If you look at the ray is moving from air into glass, then which means the ray of light is moving from optically less dense medium to a dense medium, then we can say there total internal reflection will not take place, because the condition for total internal reflection to take place, the ray of light must be moving from a dense medium to a less dense medium. Condition number 2, the angle of incidence must be greater than the critical angle. So in this case, total internal reflection will not take place. We also have a question that is talking about the diffraction grating. This is from waves, and we are told that equation n lambda is equals to d sine theta can be used to determine the wavelength of the laser light. This which of the following represent the d, the variable d? This is a distance between adjacent lines in the diffraction grating, and this n here represent the order, lambda represent the wavelength of the light that is directed to the diffraction grating, and theta is the angle between the central and the given order. Question number 5, we are told that which of the following gives distance in meters? Something that we needed to understand here for pulse echo technique is that speed is equal to twice the distance, because sound will travel, hit the obstacle, and then comes back. So which means the sound wave will travel twice the distance over that particular time that's given. And if you work it out, you are going to get our answer equivalent to 340 times 0.0030. So the trick here was understanding this formula, and then also appreciating the fact that the time was given in milliseconds, and in milliseconds that will be 10 raised to power -3 multiplied to this time that was provided. So another area that is very key when it comes to unit 2 physics, that is electricity and waves, is the concept of electricity. You will find that many questions will be from electricity. You'll see a junk of questions, and we are going to see that. Yeah, now we are told that a light dependent resistor is connected in the circuit as shown there. What's a light dependent resistor? A light dependent resistor is the type of resistor whose resistance depends on the intensity of light. If there is more light, the resistance of a light dependent resistor decreases. When you move the light dependent resistor to a dark room, the resistance of LDR increases. Now the intensity of light on the light dependent resistor decreases. Which row of the table is correct? Now in this case here, we are supposed to talk of the ammeter reading and the voltmeter reading. Now this is the catch. If the incident light if the intensity, all right, intensity incident, right? So let's go back to the main question and check. Right, we have that. Which row is correct? The intensity of light decreased. That is the key point. That's something that we really need to put into consideration. Light decreased. So if light decreases, what's going to happen? If light decreases, what's going to happen in terms of resistance of this LDR? We are going to say here, resistance is going to increase, right? So if light decreases, resistance will increase. So if resistance of the LDR increases, it means the total resistance of the circuit is going to increase. The total resistance of the circuit is going to increase. And if the total resistance in the circuit increases, it will mean that the total current flowing this circuit is going to decrease. So if the total current decreases, so the ammeter reading is going to decrease. So the ammeter reading will decrease. All right, good. So if the resistance of this LDR also increases, if resistance of the LDR increases, then it will mean if we have a voltmeter connected at this particular point, if we'll have a voltmeter connected here, if the resistance of the LDR increases, the voltmeter reading will increase also. So that means what? When the resistance of the LDR increases, the potential drop across the LDR will increase, then which means there will be less voltage, there will be less potential drop in the fixed resistor here, then the voltmeter reading will be lower. Let me repeat this because I know in May, June, question like this will smell in the exam. If the resistance of the LDR increases, it will mean the potential drop across the LDR will increase. Then the voltmeter reading will be less because there will be less potential drop across that particular resistor we are having at that point. So which means the voltmeter reading will decrease, and therefore the correct answer was supposed to be A. Ammeter reading decreases and the voltmeter reading also decreases. The diagram shows some energy levels in an atom, and we are told the electron atom is excited from the ground state to the energy level 3. How many different frequencies of radiation can be emitted from this atom as it returns to the ground state? Remember, once it's excited and it becomes at this level, the moment is going to go back, it will first emit the frequency for 3, and then it will emit the frequency for 2, and then emit the frequency for N1. So which means the correct answer there is going to be C, which is 3. When longitudinal waves pass through a material, compression and rarefactions are formed. Which of the following statement is correct? Rarefactions are the point where pressure is minimum. Pressure is minimum. Moving to question number 9, still on electricity. The lamp is connected in the circuit as shown there. In 30 seconds, the charge passing P, point P is 0.4 coulombs. Then for you to give the energy transferred during this particular time, you are supposed to remember that energy is equals to voltage times charge. You can use that formula and you get the answer correct, direct. But also you can use charge is equals to IT. You can create the current and use the formula energy equals to IVT. The reason as to why I brought all these formulas here is to enable you revise all of them, because we don't know how the exams for May, June will be tested. But I've brought now all this formula here on board so that you can be able to know them. First, we shall say energy is equals to voltage times charge. So if you multiply the voltage and the charge that passed, which is 0.4 as the charge and 1.5 as the voltage that was given the circuit, we'll get the answer direct, which is B. Or you can be able to use charge is equals to current times what? Time. You get the current, and then once you have the current, you can be able to use energy is equals to current times voltage times time. And if you simplify that, you can see now at this one point we have our answer there, which is 0.4 times still 1.5, and our answer still remains to be what? B. Then moving to question number 10, which is going to mark the end of the multiple choice section, and which of the following is not correct statement about stationary waves. So something that we need to put into consideration is that a stationary wave is formed when two waves of the same frequency and same amplitude interfere, but the two waves must be traveling in opposite directions. So for instance, if we have a wave traveling, let me just use this as an obstacle, a wave traveling to this direction to meet the obstacle, it will be reflected, and then it will just follow that path backwards. So since the waves is having the two waves are having same frequency, same amplitude, but traveling in opposite direction, then we're going to have interference taking place. And region of maximum displacement, we're going to call them regions of maximum displacement, we're going to call them antinodes, and that is where constructive interference takes place. And region where destructive interference takes place, and which is regions of zero displacement, those ones we are going to call them nodes. The distance between two adjacent nodes is going to be half a wavelength, right? So the distance between adjacent nodes is equal to one wavelength. So that is very wrong, because we were supposed to choose a statement which is not correct about stationary waves. All points between two adjacent nodes are in phase. So sometimes you'll be given a question to identify. If you are told there's a point here, there's another point here, and there's a point here, there's another point here. All these points that are labeled as red, they are in phase. And all these points down here, also they are in phase. But if you have a point which is at this point and another point is here, the two points are antiphase. The phase difference is 180. Okay, so you need to know that. Now let's change the gear and look at how to answer question to do with theory questions, and we have structured questions here. Particle traveling, a particle traveling at a speed of 9.89 times 10 raised to the power 5 meters per second as the de Broglie wavelength of 7.37 times 10 raised to the power -10. We are supposed to deduce whether the particle has a mass equal to the electron mass. We know the mass of an electron, and you can be able to check at the last page of this paper. You'll be during your exams, you'll be given the mass of an electron. There's some constant you'll be given. You'll be given Planck's constant. You'll be given mass of an electron. You'll be given what 1 electron volt is equivalent to in joules. So in this case question, you are supposed to remember this formula that lambda is equals to Planck's constant over the momentum, and wavelength lambda is equals to Planck's constant over mass times the speed of that particular particle. And if we substitute whatever that we were given, we'll get our answer equivalent to 9.1 times 10 raised to the power -31 kilograms. And this is approximately about the mass of an electron. That's what you are supposed to get. Now moving to question number 12. This question number 12 was testing waves and basically refraction of light. in the experiment to determine the refractive index of glass, a student directed a ray of light towards a glass prism. So the ray of light is shown before it enters the glass prism and after entering into the glass. Then we are told determine the refractive index of the glass. So the reason as to why most students got this question wrong is because of not realizing the angle 32 that was given here is not the angle of incidence. So the first thing a student was supposed to do is to identify a normal and find the angle between the normal and the incident ray, and that's going to be 90 minus 32, and that is going to translate to what? It's going to translate to 58 degrees. And the angle inside here is going to be 40, because the angle that was given was the angle between the glass and the refracted ray. So anytime you are going to be given questions in your AS physics exam, make sure you check the information that is given. The examiner might be tricking you on something small, then all of a sudden you end up not realizing that. You do the entire question only to realize when you are walking out of the exam room that you made a grievous mistake, and you will start doing it like this. You end up starting crying out of the exam room because of not being keen. Read the questions as if your life depends on those questions. Anyway, your life depends on that. Now, looking at that question, the formula you were supposed to use in order to work it out, because light is moving from two different media, then we're going to use this formula that you were taught in class, that N1, which is the refractive index of the first material or the first medium, times the sine of the angle in that medium should be equal to N2 sine theta 2. So in this case, where our N1 is going to be the refractive index of air, and the angle in that case we're going to get as theta 1 is going to be 58, should be equals to N2, which is the refractive index of glass, which we are looking for here, and then the angle we shall use as theta 2 is 40. Now substituting that and working it out, you are going to get your answer equivalent to 1.32. And you need to realize refractive index is a ratio, so it has no units. Then now, having looked at that, we need to look at the question that follows. Draw on the diagram the ray of light as it emerges from the prism at A. So we're going to look at that. So at A, we are having a ray moving from glass going back to air, so which means it's moving from a dense medium to a less dense medium. So that means the ray of light is going to bend away from the normal, because the ray, as it's moving from a dense medium to a less dense medium, the light is going to speed up. It's going to increase speed. Then it is going to bend away from the normal, and then we're going to have our ray traveling like that. Don't forget to indicate an arrow when you are stating rays of light. And if you are new to Prof Learn YouTube channel, consider subscribing so that anytime I'm going to work more tutorials, you'll be notified. Anytime we are going to be working physics for A levels also, you'll be in the house so that we can be able to learn and grow together. Now, a different prism is made of glass with a refractive index of 1.63. Calculate the speed of light in this. So you are given refractive index, then you are supposed to work out the speed at which light passes in this glass. So you are supposed to remember that refractive index is equals to speed of light in a vacuum divided by the speed of light in that particular medium in that particular glass. So in that case, the speed of light is c. So we are going to say 1.63 is equal to 3.0 times 10 to the power 8 over the speed of light in that piece of glass. So if we rearrange this and try to put in our calculator, we are going to get our answers 1.84 times 10 to the power 8 meters per second. That is for light. Again, we are back in electricity. We are back in what? Electricity. Equal length of copper wires, because resistance of wires depends on the length and the cross-section area. If a wire is longer, it means it's going to have a higher resistance. If a wire is having a large cross-section area, it means there are more electrons in that wire that will be able to conduct electricity, so the resistance is going to be less. Now, wire said has twice the diameter. So if it has twice the diameter, it means its resistance is going to decrease by factor 4. So it means W is going to have a higher resistance than said by 4. Right? Then explain why the drift velocity of charge carriers in this is the same value in wire W and wire Z. So what we are going to realize is that there will be more current that is going to flow in Z than in W. But in this case, I summarized that in few words and said Z has a larger cross-section area than W, so Z has a smaller resistance than W. Z will have greater current than W, and since current is equal to number of density charge carriers times cross-section area times the drift velocity times the charge of an electron, with both current, cross-section area and current greater in W, yeah, greater in W or larger in W. All right, so moving to the next question. Again, electricity is greeting us, so which means anytime you are going to be having a paper of unit 2, electricity will be very, very prominent. So which means at this particular time you need to make peace with electricity so that you avoid crying unnecessarily after the exam. So ensure you are working on electricity, you understand how to work question to do with parallel circuits, when components are connected in series and in parallel, what you do. And that is exactly what we are doing in this video, so that you know exactly what to do, so that we prevent the aspect of crying after the exam. So we are very sure that in that coming exam of May-June, there will be an electricity questions whereby you have resistors, whereby you have thermistors, whereby you have LDR, whereby you have fixed resistors connected in series and in what? Parallel. So in each of the question, the way I usually tested, you need to do more of the past papers so that you'll be seeing the trend. Show that the voltmeter reading was about 6 volts. So the total voltage that was supplied here was 12 volts. And the ammeter reading, which means the current that is running through the circuit, is 23 milliamperes. So which means if we know the resistance that we have here, of course the resistance that we have in this particular section times the current, we can be able to find the potential drop in this particular part. So total resistance when components are connected in parallel is going to be given by 1 over R1 plus 1 over R2 raised to power -1. That formula is going to give you the answer direct, right? So in this case, if I want to find the total resistance in that section where we are having 2 resistors which are in parallel, we are going to say that 1 over 500 plus 1 over 600 raised to power -1, and the total resistance in that case is going to reduce to 273 ohms. Now with this resistance that we are having at this given point, it goes without saying that we can be able now to use the current that was given. The current that was passing through the circuit was 23 milliamperes. So we are going to say voltage is equals to current times resistance. This is Ohm's law, isn't it? Then from there, we can be able to substitute 0.023. Don't forget that current was given in milliamperes, and then it means you are going to multiply that by 10 raised to the power negative 3, and that's going to give us 0.023. Then multiply the resistance, and the voltage is going to be what? 6.28, and that is the reading of this voltmeter that we have at this point. So in the event you are told to work out the PD across this thermistor, what are we going to do? If you are working out the PD across this thermistor, you are going to take the value that you have gotten, which value is that? 6.28. Then we subtract that value from the 12 volts. Okay, now calculate the power dissipated by the thermistor. We know that power dissipated is given by the formula power equals to current times voltage. So if we know the voltage of the thermistor and the current in the circuit, or the current that is passing through that thermistor, then we can be able to get the power dissipated. So if we have gotten the voltage in this section is 6.28, then to get the voltage here is 12 minus that voltage that we got here, and that is going to translate to what? That is going to translate to 5.72 volts. Then since the current was 0.023, then we can be able to multiply the two, and we shall get our answer equivalent to 0.13 watt as the power dissipated. Explain the effect of decreasing temperature of the thermistor on the ammeter reading and the voltmeter reading. This question is showing up how many times? The same question in the paper. How many times is it showing up? And you will see another one. So this means we need to understand how to answer that question, so that if it comes to an exam, we are able to answer it. We are told, explain the effect of decreasing temperature of the thermistor. The other question was talking about LDR. Now this is decreasing temperature of a thermistor. Remember, as temperature decreases for a thermistor, as temperature decreases, resistance of the thermistor increases. Let's go back. If resistance of the thermistor increases, it will mean the overall resistance in the circuit is going to increase. If the overall resistance increases, it means the total current flowing in the circuit is going to decrease. Now, if current has decreased, how will that affect the ammeter reading? Just tell me in the comment section, how is that going to affect the ammeter reading? The ammeter reading, yes, is going to be smaller. It's going to decrease. Okay? What about the voltmeter? So if the resistance here increases, it means the potential drop, the potential difference across the thermistor is going to go high. Since the resistance has increased, there will be a larger potential drop at this thermistor. Then it means the setup in this section that we're having here is going to have less voltage. There will be a larger voltage drop here because of increase in resistance. Then that means the voltmeter reading is going to go down. All right, you see such kind of questions in your exam, and I believe you've gotten value from this particular video. If you have gotten value from this tutorial, consider sharing it to your friends. Leave a comment down below if the discussion was of great help to you. Let's go ahead and mention that, and we're saying as temperature decreases, resistance of the thermistor increases, and this increases the overall resistance of the circuit. Thus, current in the circuit decreases, so the reading of the ammeter decreases. Due to high resistance of the thermistor, the potential drop across the thermistor is going to increase. Hence, the potential drop across the parallel section is going to be small, which means the voltmeter reading is going to decrease. That is just a summary of how you're supposed to put your answer in your paper when you are asked such kind of questions. Now we're moving to waves. We are having a kind of double slit experiment. This is kind of double slit experiment. Something that we need to understand when we were talking about double slit experiment, the two waves must be coherent for us to have bright and dark fringes to be formed in the screen. Coherence means the waves have a constant phase difference. They are having the same frequency, so we have to ensure the sources are the waves through the double slits have a constant phase difference, and in that case we say they are coherent waves. To achieve that, you use a single source, because if you have different loudspeakers, they end up producing sources or sounds which are not coherent. So we are not going to, and in that way we are not going to have constructive and destructive interference being so effective in this case. Now, how does constructive and destructive interference occur here? When when sound or when a wave travels from this particular end and another one travel from that end like that, wherever the two waves are going to meet, if they meet while they are in phase, then constructive interference is going to take place. If they are out of phase, destructive interference will take place. Where constructive interference takes place, we're going to have a loud sound. A loud sound will be heard there. But in the region where destructive interference is taking place, we are going to have no sound at that given point, right? So, at the central maximum here, at the central point there at X, the two waves are going to travel same distance. The two waves are going to travel same distance, and then they are going to have a phase difference of 0 or a path difference of equivalent, a path difference of 0 there. So in that way, they are going to interfere constructively, and then loud sound is produced. We are supposed to explain, and it's a third question, explain why sound becomes quiet until there is no sound. A student stood at point X. Sound is being produced here. Sound is being produced. A student stood at point X and started moving in that particular direction. Then this student is going to hear sound of alternating sound, loud sound, quiet sound, loud sound, quiet sound. Region where the student is going to hear loud sound, that's region of constructive interference taking place. And for constructive interference to take place, the two waves must be in phase, right? Where it will be no sound will be heard, or a soft sound. That is a region where destructive interference has taken place, and that's when two waves meet while they are out of phase. Now let's see how you are supposed to structure your answer in order to earn full marks. As sound passes through the gaps, they diffract and interfere. So meaning diffraction is going to take place, and when the two waves from the gaps are going to interact, interference or superposition is going to occur. At point X, the waves are in phase and the interference is constructive, resulting to a loud sound. When moving away from X, the phase difference changes, and when the waves are anti-phase, when the phase difference is 180 or the path difference is half the wavelength, the waves interfere destructively, hence no sound is heard at that given point. Interference can be demonstrated using visible light, and the student connect two filament lamps of the same power supply, and a screen is placed a given distance from the lamp as shown there. Lamp 1, lamp 2. Explain why it's not possible to create a consistent interference pattern on the screen using this arrangement. Remember that these two sources are going to produce light, and the light that is going to be produced is not coherent. These are not coherent sources. The light from the two sources is not coherent since the phase difference is not constant. So the best way that could have been achieved is for the student to use a single filament and then place two slits, then so that this light that is emanating from here is coming from the same source, and then now we can expect interference taking place. So what's my final word for you after discussing this question? My final word for you here, you need to prepare on how to answer question on diffraction grating, and also you need to prepare to answer question on double slit experiment. And if you have a challenge on how to work out question on that section, check in the description. I've added a link that is going to take you through some of the questions I've already worked in this particular channel, so that you can be able to learn how to go about that. An irrigation system uses a pump to move water from lower level to a high level. The electricity for the lamp is generated using the panel of solar cells. The panel of solar cell is 1.2 meters long and 0.8 meters wide. To pump water from the lower level to the higher level, the pump needs a minimum power of 140 watts. All right, calculate the minimum efficiency given that the intensity of light on the solar cell is 1040 watts per meter square. So in this case, first we need to remember the formula: power is equals to intensity times the area. Then we need to work out the area there, which is going to give us 0.96. Then from there we can be able to work out the power using the intensity that was provided. Because intensity is given and we have the area, we can be able to get the power as 998 watts. But the efficiency is useful output power over the total input times 100, and that's going to translate to what? 140. That's going to translate to 14%. And the reason as why we are using 140 here is because we were told for it to operate, it needs useful that amount of power. Okay. Minimum efficiency is that. Suggest two reasons why the value calculated is in Roman 1 is the minimum efficiency that will operate. Suggest why the value calculated is the minimum. So something that we need to understand there is that some rays from the sun may not be incident at 90 degrees. Remember, when it's 90, when the rays are 90 degrees, that's when we have maximum power supplied by them, or maximum how can I put it? Okay, let me just take some water so that I can be able to measure that. The solar will make use of the maximum energy from the sun when the ray is incident at 90 degrees. But in this case, we're going to get some rays will not be incident at 90 degrees in that case. Another way is intensity may be lower from the sun. The intensity from the sun may be lower due to the clouds and also fog. So that is going to affect. Light from the sun arrives in the solar cells, is unpolarized. Explain the difference between unpolarized light. And we're going to say unpolarized light has vibration in many planes, while plane polarized light has vibration in one plane in the direction of the wave travel. Describe how the student can demonstrate that light from the sun is unpolarized. So the student needs to direct light through a polarizing filter and rotate the filter. There will be no change. There will be no change in the intensity if light is unpolarized, light from the sun. Put the filter and then rotate it, then that light, there will be no change in the intensity. But if the light from the sun was polarized, then rotating will affect what? The intensity. And something also I need to mention, intensity will only be affected if you are having two filters and you are rotating them. If you are having a single filter for unpolarized light, it will not affect the intensity. But if you have two filters, meaning light will pass one filter, then when you will have the second filter, and when you rotate it, then you are going to change the intensity. All right. Looking at question number 17. Question 17, we are told that the student set up a circuit shown to determine the EMF and the internal resistance of a cell. I is the current, and R is the resistance of the variable resistor. Show that the current in the circuit, show that for this circuit, resistance is equals to EMF over current minus R. How are we going to approach this question? The first thing that we're going to look at, and we need to agree, is that from Ohm's law, we know that voltage is equals to current times resistance. So we can be able to use the current that is flowing here in this circuit, and the current is I, and the total EMF, which is E. Then we can be able to say, therefore, total current is EMF divided by the total current that is flowing through the resistor. The total current in the circuit is going to be the EMF over the total current that is flowing through the circuit. That will be the first equation for total resistance. Then we can also get total resistance by adding this resistance and this resistance, because the internal resistance is in series with the external resistance. Then we are going to talk about total resistance being R plus small r. Then once we have achieved that, we can say, therefore, this section here is equals to this part, and then we can have our answer reducing to E over I is equals R plus small r, which is the internal resistance. So if we make capital R the subject of the formula, we shall remain with our equation that way. And if you see, this equation that we have here is the equation of y equals to mx plus c. So if you are going to have a straight line graph that we are going to look at, we are going to have below here, it means if we are plotting a graph of resistance against 1 over I, then it means from this particular graph we can be able to find the gradient, and the gradient is going to represent the EMF of this particular what? Of this particular battery that was used. And the internal resistance is going to be the y-intercept. The y-intercept, which is going to be at the lower section there. So we shall work out the resistance at the gradient, and the gradient is going to be our EMF, and the y-intercept here is going to be the internal resistance, just by relating this part that we have with that. And also 1 over I is on the x-axis, so this E is going to be the gradient in that case. So this knowledge I'm dispensing at this given point is important for this unit as well as for unit 3, which is usually almost mostly the last question, question 4 for unit 3, practical skills. So determine the value of E and R. In this case, the gradient is 1.5, that's 1.5 volts, and R is the intercept, the y-intercept, and that is which is going to be what? -2. In this case, -2. This is a different graph for a different question. So our intercept here is going to represent our R there. Then we can now move down and look at the next question. The student suggested, let's look at that. The student suggested that the power dissipated by internal resistance R decreases as R increases. Power dissipated across the internal resistance decreases as R increases. How true is that statement? So as R increases, what happens? The total resistance in the circuit is going to increase. As R increases, total resistance in the circuit is going to increase. When total resistance increases, current in the circuit is going to decrease, right? Since this resistance here is constant, and we know that power dissipated is I squared R, then we can be able to say that if the current goes down, then the power dissipated across the internal resistor is going also to decrease. So looking at that, we were supposed to respond there and say that as R increases, total current in the circuit decreases. So since power is equal to I squared R and R is constant, the power dissipated decreases at that given point. The student added a second identical cell in series with the first, and the cell repeated the experiment. Add a line to the graph to show the resistance of this experiment. So in that case, we are going to have our line like that. So the internal resistance will double. So that's why here we were having 2, then it will be -4. And our EMF is going to also double. So this line is going to be steeper and is going to pass through -4. If you have gotten value from this particular video, consider subscribing, and also you can leave a comment down below if the video was helpful. All right, so now moving to photoelectric effect, and we are told that in an experiment to demonstrate the photoelectric effect, ultraviolet light is incident on the metal plate. Electrons are released from the metal plate with a maximum speed of 3.51 times 10 to the power 5. We are supposed to calculate the energy of this photoelectron in electron volts. So something that we need to remember, the energy we are talking about here is the kinetic energy of these photoelectrons, and energy is equal to a half mv squared. Substituting the mass of an electron times the speed squared, we're gonna get 5.61 times 10 to the power -20. But we are also told that 1 electron volt is equal to 1.6 times 10 raised to the power -19 joules. These are constants that are usually given at the last page of your paper, so you don't have to cram this. Planck's constant, you don't have to cram that. So working it out, you are going to get your answer as what? 0.35 electron volts at that given point. The ultraviolet light used in the experiment at a wavelength of 310 nanometer, but we know that the wave equation V is equals F lambda. Then we can be able to use that wave equation in order to work out the frequency, which means we are given the wavelength. So if you are given the wavelength, it means you can be able to use the speed of an electron. This electron travels at the speed of light. So we are going to use that in order to work out what? our wavelength. Working out our wavelength, we shall get it as 9.68 times 10 to the power 14 hertz. But we know energy of a photon is Planck's constant times the frequency. So in that case, if we multiply Planck's constant, which is 6.63 times 10 to the power negative 34, then it will mean that we get our energy as, we shall get our energy as 6.42 times 10 to the power negative 19 joules. Okay? So, anytime you are working out questions in photoelectric effect, we know that energy of a photon, which is hf, is equals to Planck's constant times the threshold frequency. And threshold frequency is the minimum frequency of a photon which can enable an electron to be dislodged from the metal surface. So which means that this is a general equation that we have. And that will mean that we have HF is equals to HF naught, which is the threshold frequency, plus the kinetic energy. So energy of a photon plus the work function. Work function is the minimum energy required to dislodge an electron from the metal surface. Yeah. So if a photon, or if light is incident to a metal surface, first, for the electrons to be removed from the surface, those electrons must absorb the work function, minimum energy. If then there is any extra energy, will be used to accelerate those electrons from the surface. So in that case, energy of a photon is equal to the work function plus kinetic energy. So for us to work out this question, first we have the energy of the ultraviolet, and then we have the kinetic energy, which we worked from the previous section here. And then if we subtract the two, we are going to get the work function. Right? So with this work function that we have here, we can compare with whatever table that we were given here, and then it means that we can see this work function that we got down here corresponds to magnesium. Corresponds to magnesium. The last bit of the question that were asked there, photoelectrons are only emitted from a given metal surface if the frequency of incident radiation is above a particular value. That's why I talked about the threshold frequency. Yeah, so not every radiation can dislodge an electron from a metal surface. Yeah, electrons will be dislodged if the frequency of that radiation is above the threshold frequency of that particular metal. So each photon interacts with only one electron, and electrons absorb energy from photons. To be emitted, an electron must receive minimum amount of energy, and that minimum amount of energy we have said is the work function, which is the work function of the metal. So photon, and the energy of a photon is usually given by what? E equals to HF. So only photons with the frequency above the threshold frequency will have enough energy to release an electron. So a student is making a conclusion here and a statement. Let's see. The student does not. The student says it does not matter what value of work function is for a particular metal. Photoelectrons can always be released if the intensity of the incident light is high enough. That is a statement of a student. That's a very serious statement, which is contradicting the whole aspect of electron emission. Something that we need to understand here is that the intensity of light is only related to the amount of electrons all photons per second. So intensity, increasing the intensity increases of the photoelectrons that will be emitted from the surface. It does not affect the energy of the photons. So this student is not correct. Yeah, this student must be coming from a banana school, or is just answering rumors. He heard what the teacher was saying. He was not keen. Yeah, so increase over the increase of intensity will only increase the number of photoelectrons emitted. It does not affect the energy of the photons. So in that case, we are saying if the frequency is too low, okay, let me just put it again. Intensity of light is related to the number of photons per second. Increasing intensity only increases the number of photoelectrons emitted, but it does not affect, it does not increase the energy of each photon. So if frequency is too low, even high intensity of light or the incident radiation cannot release photons, which means the student's statement is null and void. And that marks the end of this discussion. If you have gotten value, consider subscribing so that anytime I'll be doing more tutorials, you'll be notified, and the YouTube will notify and send a notification to you immediately, so that whenever you are going to prepare for, as you are preparing for these exams, as you are preparing for the May June exams, you will be in a good position. Good luck and all the best in your exams. Did you remember to subscribe? Consider subscribing if you have not subscribed. Also, share this video to your friends. See you in the next tutorial.